everyone. Hello everyone. I'm Abhishek. Today I'm presenting my research work, the earlier diagnosis of Alzheimer. So the Swin-Transformer based on a deep learning framework using the sparse diffusion measurement. This is the outline, whatever we have discussed today. Introduction, problem identification, goal of the research, proposal, and result and this one. Exactly nowadays, Alzheimer is the uh, very common for the old age person suffering from such kind of issues. That is a neurodegenerative disease. And nowadays, the researcher literature survey we have found out the 6.2 million people affected from that particular disease. The that what kind of a conventional method we have found during literature and all these things. It is a very time consuming and slow and requires a large number of data to predict such kind of things. So as a solution, we have tried to apply the Swin-Transformer based deep learning framework to effectively diagnosis of these things. What kind of a problem exactly? Because the diffusion weighted images is required at least 40 gradient diffusion direction to scan to identify the person suffering from disease or not. And each particular direction take the 2 to 3 minutes. So 40 multiplied 2 to 3 minutes, it's lead to approximately 3 hours. So it is very hard to a person is suffering from disease to diagnosis the 3 hours, because the diffusion tensor imaging is a very powerful neuroimaging technique, which the for the track the white matter track, which they are able to responsible to identify person suffering from Alzheimer healthy, or it is within a mild cognitive or mild cognitive impairment or middle stage between the healthy and Alzheimer. So traditional method is the required the loss of a time on this. So our goal is that we have the spatial correlation between a neighboring option. Why we have doing this one? Because till now just to consider the one particular diffusion direction and take the action. So we have considered the spatial neighboring voxel wise prediction, and also we have choose the sparse diffusion to reach up to the standard what is the 40 diffusion action is the measure, and we have a accurate. Our goal is the DTI parameter, estimate the DTI parameter. It is a time consuming. How we can do that? With the sparse measurement we can perform this one and utilize this particular for the earlier diagnosis of this one. This is our model. The traditional approach is that we have give the diffusion weighted image to that traditional particular algorithm, and it's provide the tensor. Tensor is the 3 cross 3 matrix, and here the 6 is the symmetric matrix. Here we have to take the 6 component, and based on 6 component we generate the particular image. The part step 1 and step 2 both are a complement. In a first step 1, the data generated by the traditional method, because it is a time consuming. It is take the 3 hours to complete this particular process. So diffusion MRI. So we have a include a one deep learning based framework to reach up to that particular solution. How we can do that? We have a combine the T1 and T2 both images where the B value 0 and everybody know B value is equal to 1000. And this particular deep learning framework is the spatial correlation within a voxel and shifting window within a particular window. We have applied the shifting the window and deep learning technique to smartly connect and all these things how to manage. So we can and after apply the density then generate the D60 array. So what result we have found out? This is the ground truth. That is ground truth image is the photo generated on the photo diffusion weighted imaging gradient direction. In a proposed model, we have a decrease the sparse measurement we have a consider. So that here we have to take the only 21 diffusion weighted image to generate this particular model. And the LLS is the linear least square fitting. That is a traditional known as also traditional method. And after that the transformer DTA. So whenever we have a compare all these significance are there, and what is a FAADMD, that is a quantitative measure which is helpful to decide the biomarker of a particular disease. So FA is the fractional anisotropy, exogenous diffusivity and mean diffusivity. So our proposed model is the comparable to the ground truth and perform the better with the LLS fitting in the traditional. And for the check the robustness purpose, we have reduced the more number of a diffusion direction. Here we consider only 5 diffusion weighted images, and we have tried perform some more experiment. So we have found that our proposed model is the equally comparable again to the ground truth and better for the LLS fitting in traditional ETI. And traditional method is also good, but if we required the very slow process and we have required very more number of a diffusion weighted, but our model is the better in terms of when we require the less number of sparse measurement. So it is required. And how we can conclude that our model will be better? Because here with the based on a 6 component, we have a generate the error matrix and all these things. And out of a 6, we have found the 5 times and better. Whenever we have a conclude in the 21 diffusion direction, again we have a comparison in the 5 diffusion direction and comparison all these things. This time again out of a 6, 5 find better find the performance. So that's why I conclude the proposed model better in terms of it. And after the better, because it is a two kind of a classes, so we have also done some statistical and hypothetical testing. This is the image of a axial brain slice, and here we have considered the two hypotheses we have considered. The healthy patient is greater than the mild cognitive impairment. The mild MCI is the position between the healthy and Alzheimer middle stage. And second hypothesis, and in a green color we have indicated in our image, and red color also indicate the hypothesis second, where the healthy control is less than the MCI. And again we have a show more slice, the coral slice of a particular brain, and both the region defined for the Alzheimer. That's why I take the only 2 regions. Our conclusion is that the Swin-Transformer is learned better, so it is helpful for the earlier diagnosis for that. It is not directly applicable to the clinical, it is a second opinion for the doctor. And the efficient estimation of a DTI, how we can reduce this, because we are doing only sparse measurement, so we can achieve this one. The proposed deep learning framework is potential for the complex learning, because within a window we have considered the neighboring voxel also. Until now, nobody can consider the neighboring voxel. It is considered the one voxel. Why prior researcher considered only one voxel? Because it is very time consuming on a particular one point. A position is able to principal diagonality of this one. We have considered the combine on this and take the 3 crosses matrix, and based on a diffusion tensor we have decided this one. The extended framework is good for the clinical and all these things. Thank you, and kindly visit my poster. Have you any question, please?
Thank you. Any quick question?
Yeah.
So it's about the title, like it's early diagnosis of Alzheimer's. In the work, I don't see the diagnosis of Alzheimer's, but rather the generation of the MRIs using diffusion models, right?
Here we have a help diagnosis based on a quantitative measure of a fractional entropy, exogenous entropy. That is a 3 parameter quantitative measure. Based help of this decided by the clinician. Radiologist define this particular terminology, and based on a deep learning, because I am not a medical background, I am a computer scientist, so I reduce the computational cost this one, and just reach out that particular quantitative measure, and this particular quantitative measure is called as responsible for the diagnosis and biomarker of this.
All right. Okay. Thank you. Okay.
Any other question?
Thank you.
Thank you.